Hello, let us talk about this example, um, introducing the concept of average velocity and average acceleration and average distance. So let us look at the case where, let's say we have a particle moving or a system or could be an object, let's say a car or anything really that has a big enough mass to be part of classic mechanics, kind of like what we're studying airplanes, cars, boxes, football, things like that. And it moves a distance from x, say x1 to x2. So obviously, evidently, x2 minus x1 is a number, but right now we're going to call it delta x. And the time that passed, or the time between t1 and between the moment where the object was at x1 and the moment when the object was x2, kind of like a race or something, you can get those times, or you use a timer. As long as you know the times, you're gonna have a delta t, and that delta t could be 1 millisecond, could be 1 hour, could be 1 day, could be 1 month, could be whatever that happens to be. So the average velocity is the change in distance, delta x, and delta t. And this is a very useful concept because this is how a lot of things are reported. So the average mile per gallon, the average distance, the average speed, the average acceleration, the average velocity. So we use that to talk about changes in distances. But you can have also average acceleration, which is an interesting concept because say you change the velocity from x1 to x2. So now you have velocity 1 and velocity 2. So the delta v, all right, delta v, and in an average time is going to be acceleration. And this could be presented as a tilde on top, like this curve, or a straight line as average, or basically just write average. So mean could be also like mean velocity could be mean, but usually you'll find it like this or like that. So B like that is average velocity, or A like that is average acceleration. So let's look at this example. So 2 seconds are required to bring the piston rod of an air cylinder to rest. And actually this example is very useful because now, recently, well, past 5 to 10 years, internal combustion engines have a lot of tuning and optimization so that they are very efficient fuel flow and so that they have less emissions. And we can talk about that one day, but granted, there are electrical vehicles now trying to even perform better in terms of optimization of the way we use energy. But forget about electrical vehicles for a minute because they don't use pistons like the way internal combustion engines do. They don't use the combustion of a piston, the compression of a piston to create combustion. But let's talk about when we talk about the engine, for instance, the tuning. Let me draw over here. The piston, let's say a V, an engine with piston in shape of V, because you have line and all you have also pistons coming up and down in a direction, kind of like forming a V, right? So V6, V8, etc. So pistons and will be, if it's 6, there's going to be 3 on here and 3 over there. So like if you look on the top view, you're going to be seeing 3 pistons like that. And they all move in a synchronous manner so that when one of them is down, the other one is up, etc. But that timing is very special, very critical, so that they hit the combustion chamber, or they create a combustion at a precise moment, and with the precise ratios so that your combustion is optimized to get the right fuel consumption and the best power output, etc. So this kind of problem is actually a real problem that you can encounter if you go for mechanical engineering, because it's not going to be given as a function. You're gonna have to take experimental data, and the experimental data from there you choose if you get a acceleration function as a function of time, and then do whatever we do usually, um, like up to now, or you built in the computer for the car, the engine computer system that monitors the combustion. You can build the code that will look into this and say, okay, well, maybe this way of driving I need to adjust the way I'm injecting fuel, and those things are real. Those things are programmed into your computer system in your car. But for that, you cannot use a function like that, because you cannot derive and integrate real time in terms of the way we know calculus. A computer can only do subtraction and addition, multiplication and division. So if you want to build this code for your car or for a system, you need to provide a table of data points, and that's what we're gonna do. We're gonna see how that's built. So the example says 2 seconds are required to bring the piston rod of an air cylinder or an engine. You can think of an engine if you want. So it takes 2 seconds to bring it to rest. The acceleration of the piston during those 2 seconds is as shown. So they took experimental data, and it seems like the delta t they used was 250 milliseconds or 0.25 seconds, and they noticed that they have an acceleration decreasing like so. So in 2 seconds the acceleration decreased, and if acceleration of a particle or a system, in this case a rod or a cylinder, is decreasing, then obviously you're losing acceleration, right? So don't forget about this negative sign. This is moving and is trying to get to rest. Okay, so we can use that data for everything that we need to do. They're asking the initial velocity of the piston and the distance traveled by the piston when it's brought to rest. Okay, so what I'm going to do is I'm going to use a graph to show how to build my table of velocities, accelerations, and distances. So we understand the problem, I think, right? We know what to do. They're asking us to find the acceleration, the velocity, and the speed, the distance that piston traveled as a function of time. But we're going to use average values, not continuous values. And for that, what we need to remember is this relationship. Also, we can use data that we already, equations that we already know, such as if we want to find the delta, the average, or the change in velocity from acceleration, what we need to do is get the acceleration from the average that we have, multiply time the step, the change in time. So in this particular case, the step is always the same, but you can have different steps, so be careful what they give you. And the step is going to be 250 milliseconds, or if we're going to type seconds, is 0.25 seconds. Okay, that's good. All right, so let's build this table so that we can understand how to do the average acceleration approach. All right, so the first thing here is that I'm going to have a table where we're going to have time. So time is going from 0 and 0.25. Then we have 0.5, sorry, 500 milliseconds, 0.75, 1 second, 1.25 seconds, 1.5, 1.75, and 2 seconds. And this is in seconds. Okay. All right. The next thing we're going to do is build a table where the next parameter is something that we already know, which is the acceleration. And notice that the difference between that curve and this curve is that now I'm just plotting the acceleration with negative numbers. Here they said is 0, 1, 2, 3, and 4, but at the end they tell you that the axis is actual negative values. So we're going to do that. We're going to plot those values as we know them. So at 0 seconds, when the initial velocity is negative 4 meters. Okay, so first of all, the acceleration and the units of acceleration are meters per second. They could be feet per second squared, but here we're talking international units, so it's meter per second squared, and which is okay. Let's draw the table so we know where to draw. Okay, good. That one is going to be 1. That one is 0.5. All right. We'll draw as we go on. So for acceleration here, we have first is negative 4. So that was pretty simple. At 0.25 is something, I don't know, is it going to be like negative 2.5? Negative 2.5? I don't know if it's 2.5, but we're going to approximate. Then at 0.5, we have something like, let's say 1.4. Okay. At 75, we have, what is that, 0.9? Can we say negative 0.9? All right. Of course, if we have the data the measurements, then we know exactly what it is. But from now, we're just trying to retrieve this from the curve. Okay. So now we're gonna say at 1 is, I think is around 0.6, but it's negative. So 9, let's say, I don't know, let's say negative 0.5. It's between 5 and 6, I would say. Then we're gonna do at 1.25. Is that 0.4 maybe? So yeah, let's do this one is 0.6 and this one is 0.4. Okay. Then we need to do the next one, which is that, and this one, which is that. Let's do it again. 1.5. All right, 1.75 and 2. Cool. So at 1.5, what is that? 0.33 maybe? I don't know. That's tough. Negative 0.5, 1.5. Or let's say 0.15. At 175, that's going to be tough. Let's say 0.06 maybe, and then here at 2 is going to be 0. That should be pretty simple. Okay, so 2.5, they have 0.9, negative 0.6, 0.4. Well, I think that's going to be close enough to what we need. All right, so the next thing we need to do is find out what would be the average velocity. And that, so what we're doing right now is finding each point on the grid. So this is going to be acceleration from point 2 minus acceleration from point 1. And that is going to be divided by 2. Okay. All right, so between these two, we have, so 4 plus 2.25. Sorry, it's not that. It's 4 plus 2.5, and that divided by 2. Okay, 3.25. But since we have negative values in this acceleration, we're going to do negative 3.25. So we know that everything here is going to be negative because we're talking about accelerations, which are negative. Okay. Then the next one is 2.5 plus 1.4 equals divided by 2 is 1.95. So 1.95, taking those two. The next one is 1.4 plus 0.9, and that is divided by 2, 1.15. Where's my pen? 1.15. No, it's not 11.5, it's 0.15. Okay, 1.15. Then the next one is, so 0.9 plus 0.6 is 1.5 divided by 2, 0.75. The next one is 0.6 plus 0.4 is 1 divided by 2 is 0.5. All right, 0.4 plus 0.15 is 0.55 divided by 2 is 0.275. All right, so 0.15 plus 0.06 is 0.21 divided by 2 is 0.11, or well, 0.105. And lastly, these two, which is 0.03. Okay, so we have these acceleration points. All right, let me go ahead and get rid of something else, which is that formula here, so we can keep building our table. All right, so the next thing we're going to do is we're going to talk about our, well, we're going to talk about our velocity, but I need to create this part first. Okay. All right, so the next one is going to be our velocity. It's going to be our average velocity. So that will be our delta V in meters per second. And in that case, is going to be pretty simple because we already have the acceleration and we have the time. So delta V, as we said before, will be the average acceleration times delta t, right? Because if we look at this formula, we have meters per second squared And if we multiply times second, then it's meters per second, which is velocity. Okay, so let's do that. All right. Okay. All right. Let me fix this a little in case you just want to look at the file later on. Okay, so this is A1 plus A2 divided by 2. So this is two accelerations, which basically, if we look again at the plot, it will be that one plus that one divided by 2, right? That will give us an average acceleration. That one plus that one divided by 2, that will give us an average acceleration. The average acceleration is plotted right there. Okay, so let's go ahead and get our velocity.